Okay, so we have just a quick answer key explanation for a physics rotation test for mechanics. So you've got a girl. We don't know the moment of inertia of her center body, but we do know the moment of inertia of the weights and the arms. So the moment of inertia of the two weights extended, and then she's going to bring them into her body, and then the moment of inertia of those weights and her arms will be less. Okay, and that data is listed here. So the extended moment of inertia of her arms on the weights is 6.70 kilogram meter squared, and close to her body is 1.68 kilogram meter squared. So, but we don't know the moment of inertia of the rest of her body. So the experiment is set up so that we have different beginning angular velocities with the arms extended outwards. Then she brings her arms in closer to her body and goes faster. That's their final angular velocity, 1.17 rads per second. So this is a conservation of angular momentum. L1 equals L2. So because she's spinning around an axis inside her, we will use I1 omega 1 equals I2 omega 2. So I1, of course, is the girl's moment of inertia of the center part of her body, plus her weights and her arms extended. And then I2 is the moment of inertia of the girl's body, plus the weights when they're closer to her body. And we just have omega 1 and omega 2 here. Now what I did is I solved for omega 2 by just dividing this part to the other side. Okay, and then I graphed on the y-axis omega 2, and then I put omega 1 on the x-axis, so that I could get a line of best fit to the data, and that's what it is by regression analysis. The slope then is 2.33, will equal the moment of inertia of the girl isolated out as an x, plus her arms extended, divided by the moment of inertia of the girl plus her arms closer to her body. And the slope is 2.33. I solved for x and got 2.09. So 2.09 kilogram meter squared is the moment of inertia of the girl's body, the center part of her body. It does not include the weights or her arms. Now it's later discovered that friction force between the girl's skates and the ground cannot be ignored. So that means she's going to slow down. She's going to look like she's got more moment of inertia because she will resist changes in motion even more because of that friction force. So the experimental value of the moment of inertia will be greater than her actual. Okay. Now to determine the frictional torque for the girl, okay, we just simply let her start rotating and we measure the time for her to come to a complete stop. Okay, so that makes it pretty easy for us to do. Okay, so what we've got then is omega final, which is 0, equals omega initial plus alpha t. And then solving for alpha, we get 0.429 rads per second squared. Okay, now to get the torque for that, torque equals I alpha. So we take the entire moment of inertia of her body plus her arms extended, because this is where her arms are extended, and we multiply it by that angular acceleration, okay, to get the torque, which is 3.77 Newton meters. Okay, next question here. This is just simply a situation where we have a biceps muscle attached to an arm holding a weight with a hand. Okay, so we have an 85-degree angle, I think is what it says, okay, which then is only a 5-degree angle relative to the vertical. Why do we want the vertical? Because it's the perpendicular component of our force that allows us to have torque. So there's a torque upwards because of the biceps and 2 torques downwards, 1 because of the arm and 1 because of the weight of the mass. And what are we going to do? We're just going to take the sum of all torques equals 0. The biceps will be force tension times the distance of 0.03, multiplied by the cosine of 5, because that will give us the vertical component, minus the torque because of the arm. Notice how we're taking the distance to be half of the 35 centimeters, because that will occur right in the middle. And then 50 newtons times 0.35, which is the total distance of the weight to the point of rotation. And then solving for force tension, we get 641 newtons. Now again, if we go back up here, we have we need the perpendicular component to that force, okay, for the biceps only. That's what causes torque. Okay, the final question, okay, on this review, we have a wheel comprised of an outer rim and then 3 spokes in the middle. And our job is to find the moment of inertia of the entire thing. Okay, so let's take a look at our spoke in the middle. We do have a lambda equals mx over 6L squared. Okay, well then we need to solve for the moment of inertia of this. Now remember, the moment of inertia is equal to the integral of dm, okay, multiplied by r squared. Okay, so let's see what that should look like. Okay, well, if we look at this here, dm is going to be equal to lambda, okay, times dx. Okay, well, lambda here is mx over 6L squared. And that's what I'm going to put here. Now notice that those are constants here, so I'm going to put that out of my integral. I've got an x, so I'm going to be multiplying that x multiplied by x squared and then times dx. So here's my integral that I set up, okay, to find the moment of inertia of that. Now, of course, I'm going to integrate that. Okay, x cubed is x to the 4th divided by 4. I'm integrating that from 0 to L, the length of the entire spoke. Okay. And then I'm just going to put L in there, and then I will easily get L to the 4th divided by 4 there. Okay. And that becomes ML squared over 24 once I cross my L squareds off and multiply by 6 times 4. Okay. Now, our final answer then is MR squared, okay, over 24. Okay. But there are 3 of them. Okay. So then I need to multiply this times 3, because there's 3 spokes. Okay. And then plus the outer rim. The outer rim has a mass of m, and we're just going to multiply that by the radius. Okay, so that's just mr squared. Now I am replacing L with R in this case because the length of this spoke is equal to R. Okay, adding that up, I get 9/8 mr squared is the moment of inertia of that. Okay. Now, if a force is applied to the edge of the object for a time t, so I have an expression for the final angular velocity, assuming this starts from rest. Well, remember, torque equals I alpha. So torque is force times radius. Here's my I, and then multiplied by alpha. Alpha is 8F over 9mr then. To get my final angular velocity, I make a final equals 0 plus my angular acceleration times time. And I get 8 over 9 ft and then divided by mr. And it wants the final angular kinetic energy or rotational kinetic energy. Okay. Well, kinetic energy rotational is 1/2 I omega squared. So 1/2, here I put my I in there, and then here's my omega, and I square it. And then cancel everything out. I get 4/9 F squared T squared divided by m. And that is our review.